Hello everyone, I am Dr. Muhammad Salim from School of Electrical and Electronic Engineering, University of Science, Malaysia. I'm here to present our paper at remote session, paper number 12 of the Conference of International Conference of Environment and Electrical Engineering. The paper title is Fully Bridge Three-Phase Interleaved Multi-LLC Resonant Converter for High Voltage Applications. The paper is authored along with Professor Figna and Professor Sanjay Kumar and Professor Lewinsky and Professor Fagata Yaramasu. So we start with presentation outlines, which is introduction, the proposed circuit configuration, circuit analysis, numerical test and discussion, and conclusion. Start with the introduction. As it was known recently, resonant converters have gained interest due to their ability to function at high frequency with high power density and also efficient conversion and smooth waveforms. Hence, resonant converters have been developed and utilized to meet the strict demands of the power industrial applications, such as renewable energy systems, smart grids, battery chargers, and hybrid electrical vehicles. In general, resonant converter can be classified into several categories, such as resonant network structure and element count. What we mean here about the network structure is about the structure of the tank, whether it's connected in series, parallel, and also the count of elements. Right? The element count means like two element resonant tank, three resonant limit resonant count, and four, and so on. Right? Also, the conduction mode or resonant converter can be work under conduction mode and discontinuous mode, and also adopted of the soft switching technique. Okay, based on the frequency ratio, our resonant converter can be work under 0 volt switching or either zero current switching based on our switching frequency. Although single stage resonant converters are well established and advanced in industrial application, they still face some challenges, especially in high input voltage application. This is because of the current stress on the switch device, which caused notable reduction in both efficiency and reliability. Therefore, three-phase and multi-level converters have been preferred because of their ability to utilize low voltage rating switching devices for high voltage application. Three-phase interleaved LLC resonant converter have been considered in literature. It consists of three fully bridge LLC resonant converters with a set of secondary part combined using connected diode rectifier. Right, which three-phase rectifier here. Right. Hence, the converter is suited for high voltage application with zero voltage switching for all power switches. Right. Through LLC resonant converter, LLC converters has many advantages over conventional topologies. It requires many output filter capacitor to maintain the output voltage level, especially in high current and low voltage application. Therefore, the two-phase interleaved LLC converter have been proposed so that the conduction losses and the output capacitor value can be reduced. So based on all these reasons, this work successfully modified three-phase interleaved multi LLC converter with full bridge rectifier for high voltage application. The succession of this converter yields a high gain of output voltage with wide load variation and zero voltage switching ranges. Right, this can achieved by using identical value of LLC tanks with step-up transformer that are connected in series to ensure the current balancing and to obtain wide range of zero voltage switching and high voltage gain. The proposed circuit configuration. Alright, as we see here on the circuit configuration is figure 1, which shows the schematic diagram of proposed three-phase interleaved multi-LC resonant converter. As we see here, three-phase inverter. Alright, three sets of three-phase inverter. They are connected in parallel with the input voltage. Alright, and each inverter here is loaded with two resonant tank. As you see, LLC, the resonant tank, and also the magnetizing inductance, which produce LLC tank. So each inverter has double LLC tanks with two transformers, right? For all three sets inverters, and the output of our transformers, they are connected in series along with full bridge rectifier. Alright, as we assumed here, our tank's parameters are identical, right? Which means like LR1 is equal to LR2, LR3 to LR6, and also all the capacitor resonance are the same value. Also, the magnetizing inductance for transformer all have the same value to simplify the analysis, and also to produce the same resonant frequency to avoid any interfacing between the different frequencies. Alright, and by utilizing the transformer magnetizing inductance, alright, so we can ensure, like, we can expand our inductivity region. So means we can ensure that our resonant tanks behaves inductively, so all our switches for each inverter can turn on until zero volt switching. So we have three sets of inverter, means 18 all our 18 primary switches will achieve zero voltage switching. Right. So as usual, we have here six sets of LLC resonant tanks. As we want to simplify, as we see in figure 2, the AC equivalent circuit of 4 LLC resonant tank. Alright. So if we assume that voltage BC is applied to the fourth LLC resonant tank, alright, so the AC gain voltage can be obtained for each LLC resonant tank, and this is achieved by utilizing the voltage divider rule. Okay, so we have the input voltage and the output voltage. So this is the gain between the output voltage and the ratio between output voltage and the input voltage. So we can use voltage divider between resonant inductance and the load to obtain the gain. Alright, as we see here, we have RE, which is the effective resistance, is converted from secondary to primary using transformer winding ratio also. Alright, so based on this, we have the input impedance, which is equal to X, which are XL and XC. They are in series and in parallel with X magnetizing inductance, and also the resistor or equivalent resistor. Right, and the output inductance, which is equal to RE parallel with magnetizing inductance. Right, as we see here in equation 4 and 5. So based on equation 4 and 5, we can obtain the gain based on the resonant tank impedances, right, as we mentioned in figure 6. And also we take into consideration the N, which is the transformer ratio. Alright, and also we have the resonant frequency and the characteristic impedance, and also the load quality factor, right? Load quality factor as its function of the load, alright, and also inductance ratio, which is the ratio between resonant inductance and magnetizing inductance, and also equivalent series resistance. So by applying the resonant frequency and the load quality factor and equivalent resonant AC resonant into question 6, so we can obtain the final gain equation, as you see in 12. As we see here, the gain equation is a function of Q, which is load quality factor, and also switching frequency. The rest, they are all constant. Here we have the LR and LM, they are constant, and also the resonant frequency is constant. So the only changes here, the switching frequency and Q. So here, figure 3 shows the gain characteristics with normalized frequency for different Q values. So we obtain here the gain curves for different Q values and for the range of frequency from 0 to double of the resonant frequency. Right. So as we see here, the frequency, when the normalized frequency is larger than 1, right? So our converter works as a gain, as a boost converter for all Q values, right? For different load values. But once it's almost 0.5, as we see here, less than 0.5, when the normalized frequency is equal to 0.5 or less than 0.5, so the gain drops to 0. And also here, at the gain, when the gain is unity, alright, sorry, when the normalized frequency is unity, as we see here, for certain Q values, when the Q is 1.25 and 1.75, as we see here, the gain is quite high, cross even 50, cross 40 and 50. So by applying at this point and this load, so this might harm our converter components. So based in this curve, we can obtain the normal we can obtain our frequency range and also our load range, right? So based on this, okay, we can go to now to numerical test and discussion. And based on the figure 3, as we see here, we choose our switching frequency range from 35 to 45 kilohertz, all right? And Lm is equal to 300 microhenry, and here we have the input voltage 400 and the target voltage, output voltage 2500 volt, and here we have the Cf is equal to 4 microfarad and all our resonant tank parameters. All right. So by using MATLAB Simulink on the parameter table in this table, okay, the tree interleaved LC converter is simulated. All right. So as mentioned, all the three inverters they work simultaneously. So we show the results on one converter. As we can see here, the output voltage of one inverter is as we can see, it's clearly shown that they are exactly 120 degrees apart from each other. All right, and we obtain our current. All right, and also we applied we have applied the frequency control, all right, variable frequency control to control our load, so to obtain wide load variation with our range of 35 to 45 kilohertz. All right, so as we see here, this figure 5 shows the simulated waveforms of the resonant current from IR for all resonant tanks. All right, from 1 to 6, we have 6 pieces of resonant tanks. All right, so the system was tested on different load conditions to confirm the control the response and the theoretical parts of the resonant currents, as shown in this 5, where all resonant currents are balanced. All right, as we see here, all these currents are balanced and has the same value as well. All right, the resonant currents, okay, as we see here, the resonant currents are decreased at full load condition. Here at the full load condition. All right, so at around this here, around 0.35 or something, 0.35 second. All right, at this point, 0.35 second. All right, our load is dropped to almost 36% of full load. All right, as you see here, the current. Right, we take a sample from here. As you see, the current almost now has double the value. The current have been increased. Okay, once we return to the full load again, and at second point 65 second, as you see here, the current drops again to its full load value. Alright, and even the load has been changed. Alright, we can see here the currents. We can see here all the currents still maintain their sinusoidal behavior. Right, and also for the capacitor voltage is response to the load change as shown in figure 6. As you see here, for figure 6, right? As we see here, also the at full load, at the full load, and also here we have 36% of the load. As we can, the voltage is still keeping its sinusoidal waveform, but the voltage have been the value have been increased. So that means our resonant capacitors behave and along with our controller to deliver the exact power. And also to validate the occurrence of zero voltage switching, the gate voltage and collector meter voltage have been measured for each switch, and we show here for only one inverter, as we have here like 6 switches for one inverter. As we see here, the collector emitter voltage drops to 0 before the voltage gate switch on. So which would achieve 0 volt switching on. So as we see, all the switches achieve 0 volt switching, 0 volt switching for all the switches. Okay, based on the gain curve shown in figure 3, the proposed converter have been proven the capability to provide a wide load variation with high output voltage for the switching frequency range from 35 to 45 kHz and the load factor from 0.25 to 1.75. As we see here in figure 8, we see here the output voltage and also the output load, the current. Alright, as we see here at the second point, almost 0.35, our load is dropped to 36% of the load. Right, so from 2.77 ampere to 1 ampere. Alright, and the voltage is still remaining the same. Even we have the overshoot here is almost like 300 or 400 volts. Alright, but the first remain the same voltage. And also here, as we can see here, the frequency have been changed. Right, as you see the rebel here of the output voltage, the frequency have been changed to accordance to achieve to remain 2500 volt. And also at this point, at this point 0.65 second, our load returned to its full load value, and as you see here, the frequency have been changed to keep our target voltage. Alright, at the conclusion, this work succeeds a three-phase interleaved multi-LLC resonant converter with variable frequency control. The primary aspects of this succeeded converter is to yield much higher voltage gain compared to the conventional LLC resonant converter, which means that the proposed converter is suited for high voltage application. The succession of this converter is also to improve all resonant tanks inductively to obtain 0 volt switching for all switches, with the aim to eliminate the switching losses. The variable frequency control was adopted to provide a wide load variation, as the gain equation is a function of switching frequency. And also finally, the result, as we see here, the results have confirmed the working principle of the performance of the succeeded converter. Thank you for your attention, and for any question please email at salim@usm.my. Thank you very much.